Hi everyone, I'm excited to introduce our recent work on characterization of path SmartNIC for accelerating distributed systems. This is a joint work with my students and colleagues at IPAS. So modern applications are demanding low latency as low as microsecond scale. In response to these high requirements, modern data centers are deploying fast networking technologies, including RDMA and SmartNIC. Their speed up in recent years has even outpaced the speed up of CPUs. RDMA is a popular choice for distributed applications recently, which has shown great performance improvements. From a systems perspective, RDMA provides two networking functionalities. Two-sided RDMA is similar to message parsing in traditional networking, which provides a send-receive primitive. One-sided RDMA provides an offloading primitive, in which the network card can read and write the server memory without involving host CPU. So suppose we have a key-value store application with a key network operation Git, aiming to retrieve the value corresponding of a key stored as server. So traditionally, the client sends a message to the server CPU using TCP/IP for execution. After receiving the request, the server CPU traverses the in-memory index to find the location of the value and return the value to the client with another message. So this process usually requires high throughput and low latency. So to enable RDMA, a straightforward approach is to replace the communication path of TCP/IP with two-sided RDMA. However, this approach has one drawback. The server CPU may become the bottleneck. So in our evaluation, a 200 gigabytes RDMA NIC can process 150 million messages per second, while the server can only provide 70 milliseconds per second, not including the CPU time to process the key-value store requests. This comparison is unlikely to change given the fact that the NIC is improving at a faster rate. So another alternative enabled by RDMA is to use one-sided RDMA primitive. Specifically, executing a key-value store or a key-value request only needs to read in the server's memory to find the index and then return the value to the client. Both steps can be done with one-sided RDMA. It has the benefits of bypassing the server CPU by offloading the computation to the faster NIC. However, a significant drawback is that network amplification. So to execute a single key-value store request, more than one RDMA request is used need to complete the task, which can degrade the overall performance utilization of the network. So the limitation of RDMA is that its offloading options are restricted by the NIC ASIC cores. So in response to this, modern NICs are extending the RDMA NIC to equip with programmable computing units, such as SoC cores. These units enable developers to offload more complex application logic onto the NIC. So with the help of the SoC, it is possible to offload more complex key-value store requests to the NIC, addressing the network amplification problem of one-sided RDMA, while avoid the CPU bottleneck of the two-sided RDMA. Specifically, we can send the request to the SmartNIC SoC to help execute the request. However, our initial results show that when we simply offload these requests to the SoC, SmartNIC accelerated key-value store can achieve only 14% of the performance of RDMA accelerated key-value stores. So the problem can be the weak computation power of the SoC or the hidden performance attacks introduced by the SmartNIC hardware. So to find the problem, we decided to first characterize the SmartNIC before using it to accelerate distributed applications. So by examining the usually incomplete documentation of SmartNICs and conducting extensive measurements, we discovered that the hardware architecture of SmartNICs are much more complex than what we have previously thought. If developers do not carefully consider these factors, they may encounter unexpected performance anomalies. Specifically, SmartNIC doesn't simply add the SoC onto it. The SoC is bridged with NIC ASIC cores with a PCI switch, where there are two PCI channels linked to NIC cores and the switch with the host together. Meanwhile, the SoC itself is also complex with memory hierarchies and some accelerators. Note that our study primarily focuses on this kind of architecture, which is usually termed as off-path SmartNIC. So there have been valuable measurements studied in the literature that analyze the performance of SmartNICs. Most of them focus on the SmartNIC's programmable computing capabilities. A well-known finding is that the computing capability of SmartNIC is weak except for the limited accelerators. So this observation is unlikely to change due to the power constraints of the NIC. Therefore, we take them as a premises during our study. However, the communication performance features of SmartNIC have not been well explored, which is actually essential functionality of a network device. So understanding them is definitely important. So the communication path of SmartNIC is much more complex than a traditional NIC. Specifically, traditional NIC only provides a single communication path to the system, which it connects the outside world network traffic to the host CPU and vice versa. SmartNIC also provides such capability. Meanwhile, SmartNIC enables more paths, including communicating with the onboard SoC memory and cores. Meanwhile, the SoC can further communicate with the host and vice versa. So characterizing these paths are the focus of this work. So more specifically, our characterization aims to answer the following two questions by measuring the performance of path SmartNICs. First, what is the performance implication of the off-path SmartNIC hardware architecture? Second, given these implications, how can system developers better utilize it? So our first finding is that extending an RNIC to the SmartNIC will slow down the path 1 performance in terms of latency and throughput. This is because extra hardware components, that is the PCIe switch and the PCIe link, are added to the critical path of each network packet process. Our empirical results show that the passing time will increase a request latency by approximately 300 nanoseconds. The delay is not negligible considering the low latency of RDMA, which operates at microsecond scale. Compared to path 1, path 2 has much better RDMA performance except for send receive, which is bottlenecked by the weak SoC computation power. Path 2 is faster because it omits passing one PCI channel from the switch to the SoC. Specifically, the PCI switch directly links to the SoC with a faster internal connection other than PCIe, thanks to the close packaging of the NIC hardware. So path 2 is faster. The weak hardware capability of a SoC may introduce anomalies even to packets not sent to the SoC itself. For example, when issuing large RDMA reads to the SoC, we observe a performance collapse on path 2. We suspect it is due to the head-of-line blocking, as more PCIe packets need to be processed at the DMA engine for large reads. One may wonder why path 1 doesn't suffer from this phenomenon. This is because due to the more powerful host CPU, path 1 can support a 4 times larger PCIe maximum transform unit compared to the SoC. Consequently, it only requires processing 1/4 of the PCIe packets, which is much smaller than path 2. So next, we explore the performance features of path 3. Interestingly, SmartNIC provides several alternatives for path 3, and each alternative has different trade-offs. The most straightforward option is to use RDMA to communicate between the host and the SoC. However, the option has higher latency than the others, even though it doesn't go through the network. Why? Because to support the RDMA protocol, packets must first come to the NIC core for processing, then to transfer back to the SoC or the host. The transfer is necessary, the additional transfer cost is non-negligible. To make the matter worse, RDMA can overuse the PCIe bandwidth between the PCIe and the NIC. This occurs because a single unidirectional traffic will occupy the bidirectional bandwidth of PCIe. What anomaly may be caused by this phenomenon? Let's consider a typical offloading design, where the client offloads a piece of data to the SoC for processing, and then the SoC sends it out to the host. This design is adopted by the state-of-the-art SmartNIC accelerated systems. For the targeted application, a system requirement is to saturate the network bandwidth, but such a design may fail to do so on our NIC. Why? From a more zoomed-in graph, let's see what happens. In the path 3, a single piece of data will pass the same PCIe link twice. This may seem not to be a problem if the PCIe bandwidth PCIe is bidirectional. However, the SoC may concurrently issuing the path 2 request on the same link. So there is performance interference happening between the PCIe, and you can only achieve half of the PCIe link. So our evaluated NIC, the half of PCIe is 128 gigabytes, which is lower than the network bandwidth. So is there another alternative to path 3? Yes, the SoC provides a DMA primitive for communication between the SoC and the host. Using DMA bypass the NIC cores and its PCI channels, resulting in lower latency and better PCI utilization. But is DMA always better? The problem of DMA is that it has a lower throughput because it relies on DMA engines on the SoC cores for execution. Due to the weak capabilities of the SoC, DMA on the SoC is orders of magnitude slower than the engines at the NIC cores, which are used by RDMA. So this results in a trade-off between throughput and latency for path 3. So in summary, the key takeaway from our findings are as follows. The path of SmartNIC is not faster than its corresponding path in a dumb NIC, and there are performance tax paid to being smart. Furthermore, each pass has performance anomalies that developers need to consider when using SmartNIC. So regarding to pass 1, the hardware that supports programmability will make the critical path longer. For pass 2, although it is faster than pass 1, it has anomalies such as using more PCIe packets. Note that there are more anomalies revealed in our paper. For pass 3, it is evident that neither RDMA nor DMA passes are perfect for achieving both low latency and high throughput. So back to our previous example, our analysis shows why simply offloading the KVR store logic to the SmartNIC is slow. First, the computation power of those SoC is weak in processing KVR store requests. Second, the communication required to read the KVR store content, namely pass 3, is inferior both in terms of throughput and latency. So a more interesting question to consider is how we can improve the acceleration of KVR stores by using SmartNICs. We have made one key observation. The powerful NIC cores on SmartNIC are underutilized when we simply offload the logic to the SoC, which opens new design spaces. More specifically, since a single communication path is unable to fully utilize the SmartNIC, we can take the advantage of unused resources on the SmartNIC to achieve better performance. For example, after saturating the SoC on the SmartNIC, we found that the NIC can still handle 127 million RDMA traffic for the KVR store. So based on our observation, we further characterize the concurrent usage of communication passes of the SmartNIC. First, if both clients use pass 1 and pass 2 alone, they would hit a similar performance bottleneck at the NIC core. Nevertheless, if we dispatch the clients to different passes, they can typically achieve a higher performance. This applies to both RDMA reads and writes. We suspect that NIC cores internally reserve some NIC cores for different passes, so a concurrent use of them can make a better performance. Moreover, concurrently using the internal and external links of SmartNICs, namely using pass 1 and pass 3, or pass 2 and pass 3 together, can achieve a better aggregated bandwidth, even higher than the network. Note that we still need to take care of the network interference. RDMA is not a good choice here due to the competition because it competes NIC cores and PCI bandwidth with other passes. So that's the all characterization of our study. Based on it, we suggest to utilize the SmartNIC as follows. First, we need to derive different alternatives to implement a given user network requests. Afterward, we need to optimize each path with the help of the performance characterizations reviewed by our study. Then we evaluate and rank each alternative based on different system requirements, namely latency and throughput. Finally, we greedily combine different alternatives until the hardware resources of SmartNIC are saturated. So let's make a final revisit to our KVR store case. So the system requirement is a low host CPU usage, low latency, and high throughput. So you can see that SmartNIC enables many alternatives for KVR store. So we won't talk about them in details due to time constraints. So based on our guideline, we next rank each alternative with evaluations. The lowest latency is achieved when all the keys values are cached on SoC because we can use one RTT to retrieve it with the help of offloading. On the other hand, the highest throughput is achieved when using RDMA to access the cached keys and values stored on the SoC, mainly thanks to the efficiency of the pass 2 on SmartNIC. So based on our rank, we choose A5 for our KVR store whenever possible and switch to A4, the second best alternative if the value is not cached. Our results show a much higher performance gain compared to a pure RDMA-based KVR store. So due to time limits, there are more reviewed NIC measurements and case studies in our papers. If you have interest, please check it out. So to conclude, SmartNIC is more complicated than a traditional dumb NIC, and we need to first characterize it before using it for our systems. This work presents a comprehensive study on a particular SmartNIC architecture of pass SmartNIC with a representative implementation of such an architecture, Bluefield 2. Nevertheless, we believe our methodology and guideline also applies to other SmartNIC architectures and implementations. Thank you for your listening.